Okay, so last time we looked at the pH calculations of some monoprotic weak acids and monoprotic weak base, and that was actually number 18 and 19. Okay, so with number 18, part A, the concentration of a weak acid was greater than 100 Ka, which allowed me to do a neglecting of the x in the Ka expression such that I could use this equation, pH equals half pKa minus half log C. And by now you've already memorized this equation. In part B, my concentration was not greater than 100 Ka, or actually it was much less than 100 Ka. And so I could not neglect x, and thus I had to do a quadratic calculation. For number 19, we had a weak base, and in that case also the concentration was not, actually it was not greater than 100 Ka, so that was not valid. And also once I did a calculation of the pH, had to be done with a quadratic equation, and I could not do it with any simplified equation. And if I had done it with a simplified equation as well, pH greater than a pKa plus 1 was also not validated. You had to have tried those equations for me to move on to number 22. With number 22, we have an example of an acid, in this case, which is very dilute, where its concentration actually is less than 0.1 Ka. And we're going to look at this acid and we're going to say that acids like this and bases under those conditions act like they are strong. So acids act like strong acids and bases will act like strong bases. These are extremely diluted acids and bases, and we're going to see why they act that way. Just beforehand, so this was number 18, we're all fine with that. With number 18, please correct the following. I had gone through the quadratic, and when I was substituting in, instead of this Ka 10 to the minus 3.2, I put another Ka value. It was the Ka of ammonia. So this is actually 10 to the minus 3.2, and this is 10 to the minus 6.2. And the pH is still okay. So number 19, we're all done with that. And we are on number 22. In this case, we have an acetic acid. It was diluted 1 to 50. When they say a dilution 1 to 50, I could have put 1 milliliter to 50 milliliters or 1 liter to 50 liters. It doesn't really matter, just 1 to 50. They gave you a pKa, and we had to, which of the following statements is correct? A, B, C, D, E. Some of the statements asked me to calculate pH, and how did I calculate it? Did I need to use a quadratic? Do I not need to use a quadratic? And did I have to look at autoionization of water or not? Well, to know any of those answers, the first thing I had to do is calculate the initial concentration after dilution. So we have to do a dilution. With a dilution, C times V equals C prime V prime. Okay, and so we have our initial concentration C, and we take an initial volume 1 liter. The final volume will be 50 liters or 50 mils. As long as they're the same units, it's fine. So my new concentration will be 10 to the minus 3 divided by 50, which is 2 times 10 to the minus 5. Now, the first thing that would come to your mind is this is very low, all right? That's a fairly low, but not too low. It's still greater than 3 times 10 to the minus 7 for, that number with strong acids. But still, let's look at now getting the pH. Well, you all know that I should check. It's a strong acid, weak acid, so I can put a table. There's absolutely no need for this table though. It's all in my mind now. Weak acids in water is C minus X, and then this is X. And so Let me check if I can, you know, ignore this x in the denominator. C divided by Ka. Is it greater than 100? Well, we check it out. Take the concentration, 10 to 2 times 10 to the minus 5, divided by the Ka, which is 10 to the minus pKa, 10 to the minus 2.9. And absolutely not. This is way less than 100, okay? Way less than 100. And so this C is not greater than 100 Ka, so that's not valid. So my X is not negligible, okay? So I have to do a quadratic, absolutely. You guys are great at quadratic equations right now. Here is my quadratic. And once I have my quadratic in, what can I do? Substitute, okay? So x squared minus kx, and I have my Ka, and I have my concentration, and simply substitute in. Multiply it all out, find your x, and what's my x? It's simply my H3O plus, get the pH. Oh, great, the pH is 4.71, and there's my answer. I have my pH. So according to what I just solved for you, if I go back to my questions, my E will be correct because pH 4.7. And in this question, it was necessary to solve a second degree equation. So D would be correct, okay? And also, in this case, the dissociation of the acid can be neglected. Well, no, I needed to use the dissociation of the acid, right, to get it. And the autoionization of water was not neglected. No, it was neglected because the concentration is greater than 3.2 times 10 to the minus 7. Okay, so it was neglected. So this answer, if I had done it like this, would be D and E. Okay, great. Well, I'll just tell you something. This is not great. Okay. This is nice. You can get the pH in a, you know, reasonable way, and this is always correct. I mean, I could always do a quadratic and get a pH. But I will tell you one thing, that we can do it a lot easier, and the answer actually will change. Okay. So this is what we did before, and now I'm going to tell you we'd used the quadratic before, and we're not going to use the quadratic. The reason we're not going to use a quadratic is because my initial concentration, or my diluted concentration, the final concentration in the solution of this acid is less than 0.1 Ka. What does that mean? It means that if this concentration is less than 0.1 Ka, guess what? I can no longer, well, I can use the quadratic, but it's better not to, okay? How so? This acid acts as a strong acid. Now remember, when I dilute something infinitely, if I throw something in a beach, you know, and in the sea, it's very logical that whatever I threw in the sea will dissociate more or less completely. Why? Because that material is so dilute. And according to Oswald's law of dilution, which is a law of dilution, which we're going to get into in a bit of detail, according to that, and according to to the fact that as your concentration decreases, your alpha increases, the alpha, which is the dissociation amount, increases, then we can say that this acid acts like a strong acid. And we're going to get more detailed into that in the class, in our class notes. But I really want you to see calculation-wise, what does this really mean? It means I no longer will use a quadratic equation, okay? And so whenever I have a very dilute acid, in this case, where this dilution, this concentration is less than 0.1 Ka, so which is this case, look, 2.2 times 10 to the minus 5 is less than 0.1 times the Ka value, which is 10 to the minus 2.9. Clearly, this is a lower number. then I will say that this is not lower than 3.2 times 10 to the minus 7. So if it's not lower than this 3.2 times 10 to the minus 7, then for strong acids, we can neglect water at this number. And under these conditions, where the concentration of a weak acid is less than 0.1 Ka, I will say that this weak acid acts like a strong acid. What does that mean? It means that this weak acid will no longer dissociate incompletely. At this very low dilute concentration, it starts to dissociate more completely. Okay, and thus the dissociation is greater than 0.99 somehow, more closer to complete. Okay? And actually, this is the idea. Look at this x. If we get the amount dissociated alpha, x is 1.96 times 10 to the minus 5. Divide that by 2 times 10 to the minus 5. Look at that. X is almost C. You know, so the amount reacted or dissociated is almost the initial amount. And so in this case, the pH is simply minus log the concentration of that acid, of that weak acid, which is like a strong acid now. So it's behaving as a strong acid. And thus my pH is simply, you take this concentration minus log the concentration of that acid after dilution, and you get, voila, 4.7. And did I need to use a quadratic? Absolutely not. I didn't. Okay, so there is no need for a quadratic equation here. And actually, the answer comes out to be A and E. I don't need a quadratic equation. And actually, I don't need the dissociation of this acid, how much dissociated. Okay, I just need its initial concentration. So A is correct. I don't need the dissociation, and E is correct. Okay, and I do not need a quadratic equation. So D is not correct. Pay attention to that question, very important one, and very nice one actually. And we just took this idea of C. And thus, back to this table. Okay, so guys, I want you to concentrate right here on the weak acids, okay? And we have now taken all this bit. If the weak acid concentration is greater than 100 Ka, I simply use pH equals half pKa minus log C. If the concentration of the acid is less than or equal to 0.1 Ka, so in this last case, number 22, for example, the acid acts, the weak acid, again, the weak acid has strong behavior, so acts like a strong acid. And depending on the concentration, in most cases, the concentration, you know, will be greater than 3.2 times 10 to the minus 7. So the pH is equal minus log of the concentration of that acid. And in between, when the concentration is greater than, less than 100 Ka, but greater than 0.1 Ka, which is the in-between value, that's when I use my quadratic. Are we clear? That's when I use quadratic. This is all you need. Memorize this. That's all you need, okay? The condition, what equation? The condition, what equation? Of course, this quadratic just comes from the Ka value. If you don't want to memorize this, that's fine. Clear? Same with a weak base, by the way. When the concentration of the weak base is greater than 100 Kb, even if they give you Ka, you need the Kb. Get the pOH in the same way, half pKb minus half log C, then get the pH, or simply use this equation, pH equals 7 plus half pKa plus half log C. If the concentration of that base is less than 0.1 Kb, just like the acid in this case, just like the example we just did, that weak base will have strong base behavior. And that weak base is so diluted, it's like I threw him in the beach. And when I throw him on, in the sea, he's gonna dissociate completely. He will no longer, halfway dissociate. He will go ahead, he will dissociate completely. Throw anything in the sea and it will, be dissociated and eaten all up. Then, in between, when the concentration is less than 100 kb, but greater than 0.1 kb, then we use the quadratic. Now, like I said, we can still calculate the pH even if I use the quadratic equation for anything. For any condition, I can use the quadratic and get a good pH. But in this course, we want you to use the conditions. When do I use a quadratic? When can I, use the other approximations, if you will? When can I use them? Do I have to use them? Absolutely not. To get a pH, you can simply use the quadratic. But in this course, we want you to actually check the concentration, see if you're allowed to do an approximation or not. Okay, sometimes when you do an approximation, you can check again, see if the pH that you got is less than or equal to pKa -1 in the case of acids. And if it is, that's great. It's like a double check. And in the case of weak base, is the pH greater than pKa +1? Now, how do you memorize this? I think of it as, I always used to make mistakes with them. It's an acid, so the pH is low, so it's less than, and put pKa -1. In the case of bases, the pH is usually higher than 7, so greater than, and put pKa +1. It's an easier way to memorize it. Great. That's the end of weak acids and weak bases. We're going to go more on strong acid, strong base questions, but I really wanted you to get a full grips of the weak acids, weak bases.